All right, now I got my stream going. All right, probably nobody's on the stream yet. I'll give it a second to warm up. That was my bad. All right, I would say we should do announcements. I just feel like no one's going to hear them online. That's okay. I tried. All right, so a couple of announcements. So this is, of course, right, our last lecture today of the quarter. So we'll just finish up, right, for an hour, kind of get through what we can get through with the acids and bases. And then I have graded last week's quiz. I just need to put them in, so I'm probably going to be scrambling to do that during your quiz period. We have the lab final today. And so if you were absent Tuesday, you can, of course, join us today on Thursday. If you are absent and not here or something, then you need to email me, like, again, ASAP, like now. And so for the online people that missed it, and I'll say it one more time, is that we need to know, again, today if we have any makeups. So, right, you can still do makeup labs next week. We just need to know today because, like everyone has kind of seen, right, these, especially the last 3 labs in this class were very difficult, right? The solutions all had to be kind of made perfectly. So the stockroom needs a little bit of time, but just let me know today. So email me, talk to me in class, whatever, smoke signal me at this rate, right? Just whatever to let me know what you need to make up. So ASAP. So I need to know that. Oh, and then other announcements. So I do have a sign-in for the quiz. So today's quiz, I'm not going to have time, obviously, to like grade them, get them back to you. And then, right, we don't really have a good place for the chapter. I was about to call it chapter 9. Chapter 20 quiz, right, of acids and bases. So today for our quiz period, I'll hand out kind of 2 quizzes. They'll probably be like practice, and then I haven't decided. We probably just want to go over them on Tuesday for review. Otherwise, I would say I'll just post the answers. But yeah, probably we'll go through them on Tuesday, so you have that to study. And again, right, you'll probably see these questions or very, very similar ones on the exam. And then, of course, we'll review for Tuesday. Our review for Thursday on Tuesday, and then exam on Thursday. And so if you're online, again, just email me for the quizzes and let me know that you were present. Or, yeah, if you watch this later, again, just email me and I can send you a copy of those quizzes for practice. And then just, like I said, email me so I can count the grade. And then, of course, don't forget about the papers. Ideally, you're turning them into me tomorrow, but if not, just ASAP. And again, I'm only looking for kind of 3 pages. A few people have kind of been asking me as well about the ACS citation. So try not to stress too much about that, right? Do the best you can, but we can always fix this later, right, if you need. And I'll try to post some resources, but like I said, we don't necessarily need to stress about this right now. We can get it perfect 3rd quarter. Other questions, comments? So I'm still catching up on grading, so I'm still behind on the labs. Slowly, they're getting done, so slowly they're happening on gradebook. And then just keep giving me all your papers ASAP for the final grading push here. All right, any questions or anything? All right, so now let's finish up our chapter. So we had left off on POH. And so we said, right, this is just another way to express our acid and basicity of a solution. And so very similar to our pH formula, we can find our POH by getting the negative log of our OH concentration. So again, that's just, right, in molarity like we've seen before. And then we can also go backwards and forwards. So if we know our POH then we can just take 10 to the negative power of our POH, and then that gets us our hydroxide concentration as well. So super useful. And then I like this graph since now we get to see a good relationship between pH and POH. So of course our pH scale goes from 0 to 14. Again, we saw that with the Kw product constant as to why it's this range. POH is the exact opposite. So 14 is the most acidic, right? 0 is basic. You can see how they add together to give us 14. So then, right, that's this relationship here. And so that's, I think I mentioned it on Tuesday, but that's what I really like about the pH chapter, is you can kind of double check yourself. So we have this relationship, pH plus POH equals 14. And then, right, you can always go back to here if you need the concentration or something. And then just a small derivation, just so you can appreciate where it came from. So, right, we said the products of the hydronium and the hydroxide concentration equal Kw, or 1 times 10 to the negative 14. Take the log of both of those. So this is, of course, you know, you plug that in. So 1 times 10 to the negative 14 gives you 14. And then the log of this, right, you can just separate and add. And then by definition, right, that's just pH and POH there. All right, so let's kind of keep going, and then we'll look at some other stuff. So then buffer solutions, and again, this, right, you always want to have Le Chatelier's principle in mind. So thinking back to our equilibrium shift. And so buffer solutions are defined as solutions that resist changes in pH when an acid or base is added. And so this works since the components of the buffer can either neutralize the acid or the base. And then by Le Chatelier's principle, right, you can find our new equilibrium. And then, so now we're seeing what makes a buffer. So then for this buffer to be able to kind of go back and forth and neutralize, then our buffer has to be a weak acid and its conjugate base. So any ideas of what an example of this would be? What's a common weak acid that we've used? Good, so acetic acid. And then do you happen to know the conjugate base for acetic acid? Yeah, acetate. So any sort of acetate salt, so sodium acetate I'll put down. But it could be any counter ion, potassium, right, etc. Lithium. So the counter ion doesn't matter too much unless, well, we'll get there. So as long as our counter ion is neutral, it doesn't matter, but we'll go over that in a little bit more detail. So perfect, right? So again, we have acetic acid, and we'll just say sodium acetate. So there's our weak acid, our conjugate base. So that's an example of a buffer. And then we could also pick, right, a weak base and its conjugate acid. So any ideas? What's a common weak base that we always see? So bicarbonate would be a good one. Now I'm totally blanking on the formula. So NaHCO3. So there's our weak base. And then what would be our conjugate acid for this one?
Carbonic acid.
Good. So H2CO3. Excellent. Yeah, we're on the ball. So perfect. So again, right, base, acid, only off by a hydrogen there. So other ones to think of, I was just thinking of ammonia and then ammonium chloride, but good, good. Lots of good examples there. And it does mention blood there. So there's our sodium bicarbonate carbonic acid buffer solution right there. as you gave. So again, excellent examples from y'all. And then, so to physically then make our acidic buffer solution, and so again, right, you guys pick the correct pairing, and so you would mix your acid with your conjugate base, and that gives you your buffer solution. And so again, we're kind of like teasing next chapter, so we're gonna like, you know, lay the foundation, kind of talk about Le Chatelier's principle, but then we're gonna save the equilibrium math for next quarter, right? So week 1, we'll get back into this, right? We'll be doing the change and the rice tables. So I'll kind of say that, right? Is like eventually this is going to rice, but right now we're just kind of thinking about it more big picture of what's happening. And so looking at this, so okay, what happens to a buffer solution when a small amount of strong base is added? And so it's kind of teasing, again, how we're going to treat this. So basically, first you kind of do the reaction, right? So you formally react it. So our base plus our acid component, so in this case, right, acetic acid. And then notice how we form the conjugate base there, right, in our neutralization reaction. So that's part of the key here. And then from there, right, again, Le Chatelier's principle, we can kind of re-equilibrate if we need to. And then, of course, the other caveat is we're not overwhelming the buffer, right? So we're saying that the amount of NaOH that's added is less than the amount of acetic acid, right? So then there's a small change. So of course you can get to the point, right, where you completely neutralize this, and then we've overwhelmed our buffer, and then of course the pH is going to increase. But like I said, we'll go through the math of all of that in kind of detail for all of these steps. And then, so looking at the opposite, so what happens to a buffer when a strong acid is added? So again, same thing, you're going to do your acid-base reaction. So in this case, HCl, now reacting right with your conjugate base. And then it's going to make HA here, or your acid, is reformed. And again, equilibrium, right, can be reestablished, so that helps, again, minimize the change in pH, right? So then we expect it to slightly decrease or not at all, again, depending how much is added. And then same caveat, right? Again, you can overwhelm your buffer and just completely neutralize everything. But otherwise, your pH change is small. And then it's just reminding us of that here. So again, we have, right, our addition of our base to our acidic buffer. And so again, we can just kind of write this out of what's going to happen. So looking at our base case, so sodium hydroxide plus acetic acid, do the reaction, right, gives us sodium acetate and water for our neutralization, right, so salt, water. And then, right, what is just telling us and how this works, so now Le Chatelier's principle. So now we have, right, the conjugate base, so C2H3O2, and then, right, it can reestablish equilibrium, so it can interact with the water then. And so, of course, some of it will reform our acid then, again, minimizing our pH change, and then form some hydroxide there. So again, right, reestablish our equilibrium. And then same thing, so we'll switch to the acidic case. So again, just writing this out more explicitly, we have HCl reacting with our base acetate, sodium acetate, gives us salt, plus now our acid, so acetic acid. And then, right, once again, equilibrium can be reestablished. So that acid will then react with water. And then in this case, right, water acts as our base. So then we make our hydronium and then conjugate base again. So again, right, we have that equilibrium that's able to go back and forth. So once we do the reaction, the new equilibrium, right, reestablished there. And so like I said, we'll get into kind of the more detailed math third quarter. But for right now, we'll look at this Henderson-Hasselbalch equation. And so this is valid when we can take our 5% approximation. And so basically, right, when we have a small change, then we can just use this relationship to find our new pH. And so then our pH is equal to our pKa. So right, you would have to look this up for an acid. For an exam, it would be provided. And there could be minor discrepancies, right, especially if you kind of look it up on the internet. So there could be small variations in the value. And then you take plus a log of the base over the acid. And then if you look at that, so just pay attention to the formula. And I think it's like on your homework where you might see it. But there's an alternate form of this equation, right? pH equals pKa minus the log of acid over base. So that's why the sign is flipped, right? Because you have acid over base. Me personally, I just stick to this formula, so I'm not confused, but then I just remember, okay, it's always base over acid, right? And then it's a plus sign. So they will get you the same answer, but again, right, don't mix them up, but that's why there's two forms of the same equation. It's just whether you're putting the acid or the base on top. And so again, this is for a weak acid solution, and this is only valid when we can do our 5% approximation. Otherwise, right, then we would have to do kind of the full Rice table. And so that's what it has here. That right now, okay, x is small. And then, right, if we can't make approximation, then we need our Rice table. And so that's just the other thing to keep in mind, right? The Rice table is always the most accurate way to approach these problems. But like we've seen, right, there's a few little shortcuts we can make mathematically when appropriate. All right, so this is probably the harder part of the chapter, just trying to understand kind of what this is saying. But I do want to back up just for a second. So before we get into this, let's just review our Ka expression, because that will help us. So we want to go back. Sorry, I was trying to find it in our notes where we wrote our Ka out. Yeah, so here's our Ka. So we were looking at our Ka here. So kind of going back to this reaction, right? We said, okay, we have our acid plus water gives us our conjugate base times hydronium. So let's go back here, and I'll just, again, rewrite that out. So Ka is H plus times our conjugate base over HA. And then let's do the same thing for our Kb expression for our base. And it might help to think about a specific reaction. And so we can look at, well, let me draw it out, what aniline looks like for you. So we have this molecule. So this is called an aniline, but right, it's essentially an amine, right, a base. And so that should kind of go off on your mind, hopefully, or start to, right? You just want to start to recognize certain patterns. So like, okay, nitrogen probably acting as a base. And so plus water. And then again, right, if it's acting as a base here, so 2 electrons from nitrogen, going to pick up the proton there, and then make our conjugate acid. So now, right, similar to like ammonium. So there's conjugate acid, right? So base, conjugate acid, and then we form hydroxide, right? So again, that's showing that this is a base since it led to the formation of hydroxide. And then we just want to write our expression. So then our expression for our Kb is then basically our HA times OH over our base, our right kind of base H here, just so you can, again, keep those things straight. So now we have our base expression. And so the other thing that we want to recognize, so then if we kind of multiply them together, sorry, where's my insert space here? So then we find that Ka times Kb equals Kw. And so, right, we can see how that works out. And we could rewrite this as hydronium times our conjugate base over HA, right? So that's Ka. So times Kb, which, right, we can rewrite as HA times OH over A minus for our base. And so now we can see how things cancel, right? So all that cancels. So that leaves us with that expression. But what this helps us do is, well, now if we have the Ka, right, we can figure out the Kb using this relationship. So that will help. And that will help us with some of the trickier scenarios there. So we'll probably see this again, like I said, third quarter, but we might need this kind of now to help us. But again, this is the main thing that we want to take away. So Ka times Kb equals Kw. And that'll help us, right, compare the relative strengths of our acid versus base equilibrium. All right, so now let's take this into our salts, and we'll go through these different scenarios. And so now, okay, let's start with this. So if the salt cation, so first we're looking at the cation. So the salt cation is the counter ion of a strong base. So that means, so looking, and I like to do this little analysis chart, especially when you're first kind of doing it. So that's the other thing about these things about acidic, basic, or neutral. Once you have already established, right, if it's acidic, basic, or neutral, then you just know, and it's always true, and you'll probably get a lot faster with them. Otherwise, I like to, again, dissect them. Okay, so let's take the first part of that statement. So the cation is the counter ion of a strong base. So then we want to look at sodium chloride. we'll look at our cation first, sodium. And then did it come from a strong base? So then you're asking yourself, right, can I just pair it with OH like that? Is that common? So yes, right? Like that's what it's implying, right? That it's a counter ion of a strong base. So yes, you can make a strong base with that. Again, meaning that it's fully disassociated, and then also meaning that this sodium isn't going to like react with water, right? So we're saying like the opposite reaction will never occur either, right? So we're not going to pluck this off or anything. So this never happens, nothing weird. So it's always going to be disassociated fully. And so that means our sodium is neutral. And then now you always know this, right? So sodium, anytime you see it, okay, that should be neutral. Now let's look at the other half of that statement. So then it says the anion is the conjugate base of a strong acid. So then let's do the same analysis. So okay, we go to chloride. Does it come from a strong acid? Well, let's look, right? We can just add hydrogen to it, HCl, and then go to your definition. And I apologize, I didn't print out the cheat sheet. I'll do that while y'all are quizzing. But so HCl, again, strong acid, right? Fully disassociated, so it's not going to reform anything. So that means our chloride is also neutral, which then gives us an overall neutral salt for sodium chloride. So sodium chloride, and all that means, right, is if you put sodium chloride in solution, it's not going to have an effect on the pH. Yeah.
Could you scroll back up to the rule for the anion?
Yeah. So then the anion is the conjugate base of a strong acid. So again, right, just try to pair that anion with hydrogen, and then you're like, is that a strong acid or not, right? Because then you just want to know if it can reform the acid or anything. So let's just go through that analysis for calcium nitrate. So again, we can kind of see how this works. So now if we do calcium nitrate, so what base is calcium from? We'll just add the simple base to it, right? Like pair hydroxide with it. So it's probably from calcium hydroxide, right? But then we mention, okay, well, this is one of our ionic compounds. We know those fully dissociate. Not that it's a part of the question here, but again, just keep in mind we are making two equivalents of hydroxide if we were trying to calculate the pH of calcium hydroxide. But just like before, so we can't reform anything, right? We're not going to reform our base. So then our calcium is neutral. Does that make sense? And then so we look at nitrate. So what acid is nitrate from? Nitric, excellent. So right, just stick your hydrogen on there. And then, okay, well, nitric, is it a strong acid, weak acid? So strong, so fully disassociates, right? So again, can't reform, which is again what it said, right? The anion is a conjugate base of a strong acid. And so therefore, again, we have a neutral solution with calcium nitrate. And again, right, you're just kind of learning, you're adding this to your bank. So anytime you see nitrates now, you know that they're neutral. And then, so okay, our cation is neutral, anion is neutral, overall salt then is neutral. So then let's do that again for KBr. Again, so we feel good about this. So what base does potassium come from? So KOH, and again, right, just a salt. so fully disassociates. So again, our potassium isn't going to do any reforming. So therefore, our potassium is neutral. And again, you're kind of learning that, right? So any of our kind of alkali metal salts are going to be neutral. Then let's look at our bromide. So what acid did bromide come from? So just stick a hydrogen to it. Hydrobromic. And then you might have to look at your chart for that one, but is it strong or weak acid? So you can go back. So that might be one of the ones we don't remember. So I need our cheat sheet printed for y'all. If I could find it here. So right, we can go back to here. Oh, and then I heard it, right? So strong acid, again, referring to our sheet of our strong acids. Okay, so hydrogen, hydrobromic acid, so good. That's strong. Again, just fully disassociate. That's why I have my one-sided arrow. And so again, right, this bromine can't do anything, can't reform our acid or anything. So it is neutral, and then overall neutral there. Okay, does that make sense for the kind of first set of situations? So now let's look at the next one. And so we still have this, okay, the salt cation is a counter ion of a strong base. But now let's look at the second half. So then it says the anion is the conjugate base of a weak acid. But then that makes the anion basic. So that's the other thing that we want to remember, right, is that the anion is going to either be basic or neutral. Oh, maybe I shouldn't write that there. So right, when like looking at these salts, again, your anion tends to either be basic or neutral when you're trying to decide. And then, right, your cation tends to be either acidic or neutral. So that kind of goes back to those general trends we talked about on Tuesday. So then again, that's what this is getting at. That, okay, well, our cation is still neutral, but now our anion is the conjugate base of a weak acid. And so then we'll see how we form hydroxide. So we'll do that right now. So let's start with sodium fluoride. And so like I said, you can start to go a little faster with your analysis, right? So we already established that sodium is from sodium hydroxide. So that means sodium is neutral. But then fluoride, so what acid does fluoride come from? Yeah, hydrofluoric. And so if we go back to our cheat sheet, right? Well, hydrofluoric does have an equilibrium. And so again, what does that mean for our salt? And might help us to write this. But again, we also want to write, well, what happens in water? So that means our fluoride salt is going to look at water, and then it's a base, right? It has electrons, so it's going to pluck off our hydrogen there. So reforming HF, right, which we said that was, again, the danger of the fluoride salts. But then here's what makes it a base, is that we form, hydroxide. And so that makes our solution basic there, right, because we have the formation of hydroxide. And so now we can say that, so then that means our fluoride is basic there, again, with the formation of hydroxide ions. And then comparing these two, so neutral, basic, and so then that makes our overall salt basic. Makes sense. And then we can repeat that process, right? So now we're looking at calcium acetate. And again, I'll still sketch it out just for clarity. So C2H3O2, so calcium acetate here. And again, same thing, we've already established that our calcium comes from calcium hydroxide. So then that is neutral. But now we have this acetate. And again, don't forget acetate could be written in kind of different forms, right? Acetic acid. So that's acetic acid. And then minus this hydrogen is the acetate. There we go. So again, just watch for acetic acid. And then, so where does acetate come from? So acetic acid, which we said was weak, right? So again, we have this equilibrium, form our acetate. And then again, we want to establish what that acetate ion is going to do. So now we take acetate plus water. And again, negative sign, right? So it can go pluck off a hydrogen. And then that reforms our acetic acid. And then makes hydroxide. So again, establishing this as a base, right, from the definition of our base of forming hydroxides. So then acetate is going to be basic. And then again, neutral plus basic gives us overall basic there for calcium acetate. Questions on that one? Seems straightforward. And so next one, so potassium nitrite. And so, right, we don't often see a lot of these nitrous, nitrite things since they are weak. At least in practice, I feel like I never see them. But again, let's go through our analysis. So potassium nitrite. So, okay, we already established potassiums from KOH. So potassium is neutral. But then our nitrite comes from our nitrous acid. And so we could go back to our cheat sheet. Oh, there's our nitrous, right? There's our nitrite there. So that kind of helps remind you. Okay. And then again, we just want to show what this nitrite is going to do in solution. And so first, let's just show the dissociation. So to form nitrite, but then that nitrite can react with water. So again, it's going to reform our nitrous acid and then make hydroxide ions, again, going along with the definition of a base that it's forming, hydroxide. So then our nitrite is basic, and then that makes potassium nitrite basic once again. All right, and then if we look, and so now this is kind of a hint too of like what you'll see. And so it tells you, okay, if the salt cation is the conjugate acid of a weak base, and then we'll kind of our limiting factors, we don't see too many weak bases in here. So again, we see a lot of amines as like our weak bases. And then the anion is a conjugate base of a strong acid. So again, that chloride, right, is neutral. So that means our cation is acidic and the anion is pH neutral. But again, right, just watch for these amines or ammonias or, so this is probably what we'll see. So let's go through our analysis. So again, ammonium chloride. And maybe it's easier, right? You could start with the chloride. You're like, okay, well, I know that that's from HCl, right? Strong acid, completely disassociated. So that means chloride is still neutral. But then this could be trickier, right? Because this is our conjugate acid. So then we have to think, well, what base did it came from? So try to think of like, right, subtracting a hydrogen in these cases. So that's what I'm saying. Always watch out for those amines especially, or things with other methyl groups. We'll see it, I think, in another example of like methylamine or something. But again, so we're thinking of, well, we have, right, ammonia, and then, right, it can react with water to make ammonium. And then again, thinking about what that ammonium then can do. So now our ammonium will look at that water, and well, now that water can act as a base, right? Pluck off one of these excess hydrogens. Now we make hydronium. So there's our acid part, right? Our H plus. And then we've reformed, oops, sorry, that I shouldn't have, I'm going to put a plus sign there. And then we reformed our ammonia, right, our base there. So, and then again, right, definition, so then we made hydronium, so that means that our ammonium is acidic from that definition. Again, the fact that we made hydronium here, so that makes this acidic. And then again, like it was saying, if our anion is neutral, then overall acidic salt. And then, so we do have a tricky situation. Well, actually, okay, sorry, jumping the gun. This, we'll kind of come back to this statement. So this says, if the salt cation is a highly charged metal ion, and usually highly charged kind of means 3 plus, but like, again, I don't want to super get into it right now because it's not as straightforward, and we're going to look at this a little bit more in detail when we look at metal structures. So salt cation is a highly charged metal, so, and the anion is the conjugate base of a strong acid, so basically, right, this is neutral. Then our cation is acidic. And that's really all we're trying to get at, is that we could have an acidic metal here, but like I said, I don't really want to get into it because this picture is oversimplified, and I think I've mentioned this in passing, but aluminum is technically amphoteric, but we'll get into that in more detail in third quarter of what's going on and how ligands can bind to metals. So again, it's kind of an oversimplified picture. All right, the tricky part, which I'm not planning on testing you on like this necessarily, but you should still be aware of how to do it or it might come up. And so what if we have this situation? So what if we're looking at ammonium fluoride, right? And so before we get into blah, 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 what they're saying, okay, well, let's look at the problem here. So ammonium fluoride, well, we just established that ammonium is acidic, right? But then fluoride is a basic salt. So now who wins? So that's our question. And then this is why I was going on this long KB, KA thing to get us back to here. And so again, it depends what we're given on an exam. So you would have to be given like the KA or KB or something of these substances. And they didn't give us anything. And so we could, right, ask the internet. So let's just see. And let's kind of walk through this. So it says that the Ka of ammonium, and let's even see what we can find. So that's the other thing, is how this is written is funny. Let's see. So I actually do get an answer. I'm going to see if it's consistent with my notes from other years. And so the problem is, like, sometimes you can look up the Ka of ammonia. And so I think the internet is saying 5.6 times 10 to the negative 10. So we'll keep that answer in mind. It says the Ka of ammonium is larger than the Kv of fluoride. Okay, well, we're still trying to get all our information. And so this is why you might need your Ka times Kb equals Kw. And so that being said, right, if this is from ammonia, usually what they'll give you is just the Kb of ammonia. So then the Kb for ammonia is 1.8 times 10 to the negative 5th. Right? Let's double check this. And again, that's where you may have a few discrepancies. Sorry, pulling up my calculator here. Sorry. All right, so let's test that out if the numbers at least are relatively close. So 1 times 10 to the negative 14 divided by our Kb. And so, okay, good, right? We just want to make sure that we're kind of consistent with our numbers. And then that's proving what we're looking for, right? So again, so Ka for the conjugate acid versus Kb, right, of the base. And then, so together, so multiplied, right, these two constants gives you 1 times 10 to the 14. Okay, so at least we're on that same page. And then again, you could look up the Kb or Ka. So I have in my notes here that the Kb of fluoride is 1.47 times 10 to the negative 11. Although you'd probably just find HF, Ka more readily. Come on, internet, go faster. So it sounds like the Ka for HF is 6.8 times 10 to the negative 4. So again, complementary. And then, so let's go back to our analysis right now that we kind of have all these numbers floating around. And okay, so now we're trying to compare our acid versus base strengths. So we want to compare, again, the Ka of ammonium, right, because it's giving, that's our acid strength. So there's our Ka. So we want to compare this number. And it says the Ka is larger than the Kb of fluoride, right? So comparing how basic it is. And so not different by much, right? But our Ka is slightly larger of 10 to the negative 10 versus 10 to the negative 11. So therefore, our solution will be acidic. But like I said, I'm probably not planning on testing you over this quite yet. It might come up. We might have I think there's something in your quiz about writing a Kb expression. So hopefully we can try that. But yeah, we'll try to keep it kind of light with this KAKB stuff. And then we are little over time or out of time, but we could still do this. So I'll kind of let people go, but we could still kind of do this as like a quick work through right now. So see if you can kind of go through these, determine if they're acidic, basic, or neutral, right? And like don't get fooled by some of these. So C is kind of tricky, but try to recognize what it is. So yeah, let's do that. Again, I know we're kind of over time, but let's try to practice that, and then I'll get the quizzes handed out. If you're online, like I said, let me know you're here. I can hand you the practice quizzes. So quizzes are just completion today. And like I said, we'll go over them on Tuesday. Does that sound good? So I'll start handing out the quizzes while you guys look at this, and then we can kind of quickly go over the answers so you at least kind of have the answers, and then you can still kind of practice. All right, so I'll flip over to this page for a second, but I'll probably at least give the answers in a few minutes and then let y'all kind of work on your quiz. All right, I'll go over the answers, but then, right, kind of, I would do the analysis on your own, especially if you're kind of struggling with this. I don't know, do people have answers at all, or probably didn't give y'all enough time? Any guesses for A or? Yeah, so that's like a good assumption, right? If it's an ionic compound and it's on our periodic table, then yeah, just assume it fully dissociates. So correct. Strontium hydroxide, then we assume, right, fully dissociates, ionic compound. So good, neutral. And then what about B? And of course, this could have been one of the special scenarios. So what was this? I think somebody whispered it. Say it louder. Say it again. But what about aluminum? Because what do we say about the? Because right, it's the highly charged metal ion. So aluminum. So then that's acidic. Yeah. So right, our aluminum 3 plus makes it acidic in this case. Good. And then again, right, bromine, hydrobromic. So that was neutral. What about this one? What the heck was this thing? Trying to confuse y'all. So right, the nitrate, of course, was neutral, so you could kind of ignore that. But well, what's this though? So remember, cations are usually acidic or neutral, and this is. Oops, sorry. I'll write it out. So close. So technically, methyl ammonium. But yeah, it does look like an aniline or amine, right? So that's your hint that like there's nitrogens attached to things, and then in your brain, right, it's going off, boom, 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 nitrogen. So then it's from something basic, but that makes the cation acidic, right? So then you kind of have to think back, okay, this is methyl, and so again, I'm getting older every day. So I don't know if you guys watch Breaking Bad, but this is what this is, or the conjugate acid of methylamine, which I don't know if you remember from Breaking Bad. They did that whole train heist thing. Yeah, so that was a compound. And then obviously this is a highly, highly regulated substance thanks to Breaking Bad. But I mean, that being said, right, it's like trivial to make meth, unfortunately. But I think I've already said that a million times in this class. I mean, literally, you just have to methylate it. That's what I keep, like, it's so easy to methylate, and okay. Keep going. I'm telling you, these methylation reactions. But anyway, so then this would be acidic then, right, from our methylamine. And then, so looking at this one, I don't know why every time I look at it, I just think of nachos, but so our sodium is neutral, but then this thing is, we probably have to go back to our cheat sheet, but it's right, chlorous acid there, or not chlorous, formate, sorry, formic acid. My apologies. So formic acid, CHO2. So just reminding us, okay, yes, there is equilibrium. So then what's this going to be? Acidic, basic, or neutral if this is from a weak acid. Basic, good. And then the last one was just that same question again. So again, right, compare. We'll just say compare Ka, Kb. And so again, right, we had found already that it was acidic. So you're probably not going to see this on this exam. I'll probably save it for next exam if I am kind of mean like this and make you compare Kas and Kbs. But At least you can kind of see where we're going. All right, questions about this? So feel free to ask me too if you need help, or ask me about anything, right? Now's the time to ask. People have also been asking to set up appointments, so yes, yes, yes. I think I need to respond to some people officially. But the answer is yes, right? So meet with me, make a time, email me. I'm available Friday, I'm available next week, right? Monday, Wednesday, just make an appointment so we can review anything. All right, I'm probably going to stop talking for now. Work on your quizzes or whatever. Make sure you signed in if you're live, right? So that's your quiz credit for today, is being here. If you're on the internet, just email me, and email me if you want a quiz copy so you can review as well. And then I'll get these notes posted. All right, any other questions? And then I'm also going to run and print out the cheat sheet that I promised. So I forgot to do that this morning, but I'll go print out this cheat sheet for y'all. 20 homework, I will grab those. I think they're in my office. All right, I'm going to stop the stream, so email me if you need something.